Welcome to Math 1314, Section 4.5. In this section, we begin to look at exponential and logarithmic equations. So, here at our first equation, we have 2 raised to some power is 32. I don't know, let's see. 2 to the 1, that's 2. 2 squared, 2 times 2 is 4. 4 times 2 is 8. That's 3 2's. 8 times 2 is 16. That's 4 2's. 16 times 2 is 32. So 2 to the x is 2 to the fifth. And so what I notice here is I now have made the bases the same. Therefore, the x we're looking for is 5. In question 2, the secret to 2 is, again, we have to remember the formula from exponents. The nth root of x to a power is writable as a fractional exponent, x to the m over n. So this fourth root of 3, all right, fourth root of 3. Well, you might say, well, where is this m thing on the inside? Well, 3 to the 1 is 3. And so this is really 3 to the 1/4 power. And so 3 to the t equals fourth root of 3 is really 3 to the 1/4. And again, you can see we have the same base now. And so we can conclude that t is 1/4. Hopefully this is making some sense. All right, question 3. We have 2 to the 3x plus 12 is 8. So the secret is we need to start with the 8. What is 8? Well, again, 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. All right, so I'm going to rewrite this 8 as 2 cubed. Well, the only way these two things can be equal is if the exponent parts are equal. So I'll set them equal. And now we solve this equation. Move the 12. 3 minus 12 is minus 9. Divide both sides by 3. And I get x is minus 3. Okay. Hopefully not too bad. So, question 4. That looks really ugly. So don't panic. The secret again is on the right hand side. So I've got 1 over 49. Well, what do I know about 49? Well, I know 49 is 7 squared. And again, I care about 7 because I see that the base on the left is 7. Now 1 over 7 squared. Well, that's one of these other facts from rules of exponents. 1 over x to the m is really x to the minus m. So a negative exponent is just 1 over x to the positive exponent. So this 1 over 7 squared is really 7 to the minus 2. So take the inside part and rewrite that. That's 7 to the minus 2. Another fact from exponents. What happens when we have x to the m raised to another power? What happens is the exponents multiply. So 7 to the minus 2 raised to the c minus 6, the exponents multiply, and I get minus 2c plus 12. All right, so at that point, the bases are the same, therefore the exponents must be equal. All right, so let's see. I'm going to move the minus 2c to the left. 2c plus 2c is 4c. I'm going to move the 16 to the right. 12 minus 16 is minus 4. And then divide both sides by 4. And so C is minus 1. In question 5, let's see. I have 8 to the 2x minus 2 is 32 to the x plus 9. So at first you might think, okay, great, I'll use 8 as the base. Well, 8 to the 1 is 8. 8 squared is already 64. So the base is not going to be 8. So what is it? We panic. Well, let's try 2. Well, 2 cubed is 8, and 2 to the 5th we've seen previously was 32. So take the 8 and rewrite that as 2 cubed. Take the 32 and rewrite that as 2 to the 5th. Now we have the stacked up exponents which will multiply. 3 times 2x is a 6x. 3 times a minus 2 is a minus 6. We've got 5 times x plus 9, so 5x plus 45. And so great, we finally do have the bases the same. Therefore, the exponent parts have to be equal. Subtract 5x, so 6x minus 5x is x. Move this minus 6 to the right. 45 plus 6 is 51. All right, and so here on question 6, we'd like to solve 5 to the y is 19. Now this is more difficult. And well, why is it more difficult? Well, 5 to the 1 is 5, and 5 squared is 25. So there's not a nice power of 5 that's going to give me 19. So we can use either logs, common logs, log 10, or natural logs to help us. So I've done it both ways so we can see we get the same answer. So you take log of both sides. By doing that, the exponent comes out in the front and I get y times log 10 of 5. Well, log 10 of 5 is a number and I can divide both sides by it. And so then I can calculate this. This looks a lot like we did with change of base. Now you can use natural logs if you prefer. In this case it makes no difference, and so natural log of 5 to the y. Same thing would happen. The y comes out into the front, and then I divide both sides by the natural log of 5. And when you calculate it, you get 1.8294828 and some more. And when you round it to 4 decimal places, that's what we get. And that seems reasonable that 5 to that power is 19. All right, in question 7. Question 7. Now the secret here on 7 is we need to clean this up a little bit before we move forward. So first off, I'm going to take this minus 9,400, move it to the right, combine it, and I get 108,400. Now we can use log 10 or natural logs, but in this case we get an added benefit if we use log 10. And that was because log 10 of 10 to something, I get it back. It does not jump out in the front. So log 10 of both sides, log 10 of 10 to this, and I just simply get back the exponent. On the right, a big ugly number. So all I have to do now is get the t by itself. So I subtract 4 from both sides and then divide both sides by 7. So the exact solution is this. The approximate solution is just to calculate this. So you're going to get log 10 of this number first, subtract 4 next, then divide that result by 7 to finally get the answer we're looking for with t. Question 8. Question 8, we have an exponential equation with e. So as in the previous problem, we need to clean this up a little bit first. So I'm going to divide both sides by 75,000. Now the good news is it gets rid of it here. 25,000 divided by 75,000 makes this now 1/3, which is a lot nicer. Now here again I could use log 10 or natural log to solve this problem, but if you use natural log, so that's this little key point here on the right, if I use natural log of e to something, I get it back. Remember that was our log b of b to something gives it to us back. So take the natural log and I get ln of 1/3 equals, I get it back, and then I simply divide by negative 0.5. And so that's the exact answer, which then we can calculate to get 2.19772 after you round it. Now I also say that it could be writable or written as ln of 3 over 0.5. Well, how in the heck did I get that? Well, ln of 1/3 is, remember our division goes to a minus. So this is ln of 1 minus the ln of 3. But the natural log of 1 is 0. So this is 0 minus ln of 3. And so you get minus ln of 3. Well, that's a minus ln of 3 over a minus 0.5. The double minuses could simplify it to look like that. Either way, you'll still get the same answer of about 2.19. All right, question 9 is hard. So you may have to look at it a couple of times to not get lost. The problem that makes it hard is I've got a base on both sides that's ugly. To use it, we can use log 10 or natural logs. Either way, I'm going to use natural log just because it's shorter to write. So I start off by taking the natural log of both sides. Natural log of something to an exponent, then this exponent can jump out in the front. Similarly, this exponent can jump out in the front. So there they are. Now where do we go from there? I have an r here and an r there. I need to get r by itself. So the only way to get my hands on r's is to distribute this natural log of 5. Okay, that's looking a little better. Problem still is I've got r here and r there. So my hope is to get them together and then factor out a common r. So take this junk on the right, move it to the left, take this minus 5 ln of 5 to the right. At that point, I at least have the r's on one side, so factor out this common r, leaving all of this stuff on the inside, and then divide. Alright, and so you could leave it like that and calculate that number. That's a little ugly to calculate, but doable. You might say what I do after this is even uglier, but let's give it a try. Now, remember we pushed numbers in the front before. You can take this number and push it back up on the top. And so this is 5 to the 5th, which calculates to be 3,125. If you take this 4, push it back there, 5 to the 4th is 625, and that's what I did. And if you push this 2 back, 7 squared is 49. So that at least makes it where I don't have to do these multiplications. Now, one more simplification we can do is, well, a difference can go back to a division. So that sort of minimizes the number of calculations I need to do. Even at that, this is not the easiest calculation, but you do get 3.1608 when you round it to 4 decimal places. Again, not easy. And it's not easy because you had back here multiple r's and you had to get your hands on them by getting them together and factoring out something in common. Alright, we switch paces now to log equations. Well, first, remember log b of x has a domain 0 to infinity. And it can't even be 0. So let's say we solve log 10 of 7 minus x equals something. Doesn't matter. And suppose I got answers of minus 2 and 9. Question is, do we keep them or throw them away or keep one of them? Well, let's see. If you plugged in minus 2, that would be 7 minus a minus 2. And you'd be taking log 10 of 9. Well, that's okay. 9 is a positive number. If I plug in 9, that's 7 minus 9, which is minus 2. And I can't have log 10 of a negative number. Why? Because the domain is only bigger than 0. So we would toss out the x equals 9, giving us only one answer, which is the minus 2. Alright. The other things that we need are log b of something equals a number. We solve that by taking b to the number equals the something. And if our problem has just logs, no numbers, just logs, I repeat, just logs on both sides, then you can conclude that the inside parts have to be equal because the log function is 1 to 1. That's why that works. Alright, so question 1 here. Look, I do have log equals log. Therefore, the inside parts have to be equal, and I can quickly get z by itself, move this z over, move the 10 over. I get 2z is 2 or z is 1. Is 1 okay? Yes. 1 plus 10 is 11. Good. 12 minus 1 is 11, which is okay too. Alright, what about question 2 here? In question 2, let's clean this up a bit. Move the 8 over. 16 and 8 is 24. Divide by 6. That looks better. And so now 2 to the 4th has to equal to this stuff on the inside. What is 2 to the 4th? 2 to the 4th is 16. And so now we can add 8 and then divide by 4. So P is 6. Is 6 okay? 4 times 6 is 24. 24 minus 8. That is positive, so we get to keep it. That's okay. Question 3. Oh, I have log plus log equals a number. Ah, a number. So I don't have log equals log. What do I do? Well, remember that when there's a plus stuck in the middle here, I can combine the logs to multiplication. So p times p is p squared. 12 times p is 12p. And so now 4 cubed equals this stuff. Well, what is 4 cubed? 4 times 4 is 16. 16 times 4 is 64. So, can we factor this quadratic equation? I don't know. Let's try. 64 is 16 times a minus 4. That would give me the minus. When I combine the middle and the outside, I do get a 12. And so I get P is minus 16 and 4. So we feel happy we solved it, but can I use both of these numbers? If I plug in the minus 16, that's log 4 of minus 16. That's not possible, so the only solution is 4. And in question 4 here, let's see. Oh, I have log of log. Log equals log. Oh, wait. There's this number there. So I don't have log equals log. So I move this log to the left-hand side. And now the difference of logs goes to division. But now I can make use of our fact that 3 to the 1 must equal to this stuff on the inside. And so 3 to the 1 is this, which is just 3. Multiply both sides by w plus 9. We're getting there. And so finally 3 times w, 3 times 9, so 3w plus 27. So now let's get our w's together and numbers together, and we get w is equal to 32. And we've made it to the end of this particular section, and we're happy.